Great. So next up, I'm excited to hear Cindy Rush talk about all or nothing phase transitions.
Thanks, Alex, and thanks to the organizers. So, okay, so just for some quick motivation. So we know in modern machine learning and high dimensional statistics, we often face regression or classification problems, for example, where the dimension of the feature vector is often much larger than the effective underlying dimensionality of the structure. So one example would be the MNIST digits, each of which is represented by a vector of 784 pixels, but it's approximated that the effective dimension is closer to the order of tens. Another example would be natural images tend to be sparse in a wavelet basis, for example. So these and other developments have justified a sort of bet on sparsity principle, which in a nutshell sort of says that the intrinsic low dimensionality is often a crucial ingredient in interpreting such high dimensional models. And so for this reason, in this sort of sparse context, what we chose to study were some central scientific questions about establishing fundamental benchmarks of problems. I probably don't need to convince this audience that these are important lines of work, but I'll say a few words introducing these sorts of fundamental benchmarks. So what we wanted to answer is, studying sparse problems, what conditions ensure that the information in the data is sufficient for satisfactory inference, and what are the most efficient algorithms for the task? So in other words, we're looking for information theoretic and computational limits, which analyze how much data is needed for various problems. If we want to perform the inference in a computationally efficient way, or if we just want to perform it at all. And so, okay, so what I'm going to talk about today in this talk is some strategies for establishing these sorts of limits, specifically in the case of rank 1 matrix estimation from noisy measurements, where we're in a setting that I'll call a true sparsity regime, where the sparsity in our signal scales sublinearly with the problem dimension. And so I'll pause to mention that low rank matrix estimation, of course, is an important problem, and it has many applications. So for example, image processing, PCA, or tensor decomposition. And while the mathematical analysis of this problem is fairly well developed, most of the study has been in the case of linear sparsity. So when the signal has a small but fixed fraction of non-zeros as the problem grows. And so what I'm going to talk about today is some strategies for looking at these sorts of statistical and computational limits when the sparsity is actually vanishing as the problem size grows. So, okay, so here's the model that I'm looking at. So we have a signal X that's a lengthened vector, and I'm assuming that the elements of the signal X are sampled IID according to some distribution I've labeled X, or sorry, I've labeled P. And when defining P, I want this to be a sparse distribution so that delta there is the direct delta at 0. And the number of non-zeros in my signal is controlled by this parameter rho, which gives the weights in this distribution. So in particular, we're in the sublinear sparsity regime, so I'm thinking that rho is going to 0 as n grows. So for this talk, I'm going to assume that this distribution P is a Bernoulli or a Bernoulli-Rademacher distribution. And so then the problem becomes, okay, one where we have access to a noisy data matrix W, and we're modeling W as a sum of a spike term, which is the XX transpose based on our sparse signal, and Gaussian noise. So the Gaussian noise is this matrix Z, which is a symmetric IID Gaussian matrix. And so in defining this model, I'm adding a parameter lambda there that we'll see must be growing, but this is going to control the signal to noise ratio of the problem. And so then my goal is to estimate the spike XX transpose given my matrix W. And so this for example, is going to build on the work that Salil talked about yesterday. It's sort of the same sort of model. Okay, so before I tell you about my results, I'll just mention some related work that we've heard about even at this workshop so far. So There's been lots of work on various forms of sparse spiked models. And it turns out that these works have played sort of a crucial role in understanding threshold phenomenon in problems more generally. However, many of them study this sort of proportional sparsity regime and not the sublinear sparsity regime that we look at here. And kind of the picture that emerged from these works is that you know, the information theoretic and the statistical thresholds actually you know, happen in very different sort of settings and very different regimes, and the gap between these thresholds actually diverges as my signal sparsity goes to 0. However, in many of these works, even for the linear sparsity regime, establishing these exact thresholds with specific constants and you know, characterizing the behaviors of the MSEs that defined these thresholds remained sort of elusive. And so this kind of changed recently. So at first, you know, Lesueur and co-authors used heuristic methods from statistical physics and in particular the replica method to observe sharp phase transitions in many problem settings. And then the rigorous mathematical theory supporting these characterizations is now largely under control. And so in the works I've related, most of the way that people study these phase transitions rigorously is either through an approximate message passing algorithm for the computational limits to tell where the message passing algorithm succeeds or fails. And then for the statistical limits, folks usually characterize the asymptotic mutual information between the signal and the data matrix in with various strategies. So some using spatial coupling, some using interpolation, and even others using like PDEs and other techniques. Sure.
I'm a little confused. I don't know if I missed something, but sorry. Okay, now I have the mic. I'm just a little confused because I'd say a fair portion of those papers are not for linear sparsity in the first group.
They're not what? Sorry.
For linear sparsity. Most of these are polynomially decaying sparsity. So like n of the alpha non-zero for alpha between 0 and 1. I mean, like actually a good portion of those.
Okay. Which one?
I mean, there's the one where my name is showing up too.
Okay, then that one we know. Okay.
That's the one that like I actually know the best, but it's for every polynomial sparsity. So n to the alpha non-zero.
Okay. Yeah.
But actually others, and then there's some low degree stuff and SOS stuff with Sam and Spade and others. I think that also talks about these polynomial sparsity regimes and stuff.
Okay. Yeah, I know that some do and some don't. You know, I think that the way that we characterize the MSEs and the sharp phase transitions is novel.
Oh, for sure. Yeah. No,
yeah.
I don't mean to take away from your stuff, because I think that for sure there's some new insights and new, like also the sharp estimates that you get and so forth are definitely.
Yeah, I'm like totally willing to admit that trying to summarize the like vast landscape of this work is a little bit challenging for me. So it could be that some of these need to be like shifted around and
Totally
where
fair. Yeah. Totally
saying them. So you know, so what I will mention is that, you know, some of the works that I am, you know, confident address similar problems to what I'm studying are those listed here. So in particular, the works that I know that address similar statistical phase transitions in the sublinear sparsity regimes for binary signals are the ones listed here. So in particular, the first two works study sort of a 0-1 phase transition of the minimum mean square error for a sparse linear regression problem that they call an all or nothing phase transition. And so what I will mention is that, you know, they study something similar in the compressed sensing problem, but they use sort of very different techniques than we do. So our work studies the statistical limits by exactly characterizing an asymptotic mutual information from which the phase transition kind of pops out as a side effect, whereas these guys tackled the MMSE directly, and they didn't say anything about about the computational limits. The other works listed are related to ours, and that they study the sublinear sparsity regime for models similar to, or the exact same as we study here, but in general, there for various reasons, the work that we give builds on there. So some of these works give heuristic locations of the thresholds, or not otherwise non-rigorous locations. So they'll analyze the thresholds by first taking, into infinity and then dropping the sparsity to 0, which isn't necessarily the same as having both of these change together. Or they don't characterize the behavior of the MSEs at all. Okay. So before I present the results, I just wanted to say exactly what I meant about limits and phase transitions. So in particular, the statistical limits and the phase transitions address questions like, under what conditions is the information and the observation sufficient for satisfactory recovery? And we'll say that a phase transition then occurs if an appropriately normalized asymptotic MMSE jumps from 0 to 1 abruptly with changing problem parameters. And how do we actually, analyze this phase transition? Well, our strategy for studying this is the following. So the phase transition is actually going to manifest itself as a singularity in the MMSE. So by singularity, I mean a discontinuity in a first order derivative. And so we get the singularity in the MMSE by actually looking at the asymptotic mutual information between the data and the spike. And so in particular, we characterize exactly this asymptotic mutual information, and then we relate it to the MMSE through the so-called IMMSE relationship, which basically says that the MMSE is equal to the derivative of the mutual information with respect to the signal to noise ratio. And so therefore, if we can get sort of closed form expressions for the mutual information, this gives us closed forms expressions for the MMSE, from which we can then find these phase transitions. To study the computational limits, we're going to study an approximate message passing algorithm, or more specifically, the asymptotic performance of the message passing algorithm. And we'll look for a place where that MSE jumps from 0 to 1 abruptly with changing problem parameters. And so just a word on why we're talking about AMP here. It turns out that approximate message passing is a class of polynomial time algorithms that have been studied for this problem in the linear sparsity regime and have shown very successful results. So in particular, in many problem settings, AMP provides Bayes optimal signal estimation. And it's conjectured that the AMP performance is as good or better than other polynomial time algorithms for problems of this sort. And so by studying the performance of AMP, we're going to say something about the computational limits of the problem. Okay, so this is a summary of which I'll just skip. It's just what I just said, but we probably don't need it for this talk. Okay, so what we'd like to do is investigate these statistical as well as computational phase transition regimes. And in particular, we're going to look at the setting where the number of non-zeros in the signal vanishes as the problem size grows, while the SNR diverges to infinity. And so I'll mention that non-trivial estimation is only possible in this problem if the SNR grows, which is perhaps not immediately obvious, but here's a quick heuristic justification. It's probably not too hard to convince yourself that the total SNR per non-zero signal component is like lambda rho. And therefore, if rho is going to 0, in order for there to be enough energy to estimate these values at all, we need that lambda diverges. And so then kind of the takeaway that I'll talk about in this talk is if we look at signals that are Bernoulli or Bernoulli-Rademacher, then the MMSE and the MSE of AMP display these 0 to 1 phase transitions, but in fact on widely different scales. So there's a diverging computational and statistical gap. Okay, so now to start presenting the results, I first wanted to discuss the scaling regimes of vanishing sparsity and diverging signal strength, in which we're able to prove these phase transitions. So these are the regimes where we're able to characterize these MSEs exactly. And for the statistical phase transition, so the information theoretic phase transition, what we need is that rho goes to 0 more slowly than into the negative beta, where beta is small enough. And then we observe a phase transition for lambda growing like negative log rho over rho. And the phase transition occurs as a function of this gamma parameter here. And then the computational phase transition is slightly different. So here for to prove the MSE of AMP for the computational phase transition, we need rho to go to 0 more slowly than log n to the negative alpha, where alpha is a parameter larger than 1, and we need lambda to grow like omega times 1 over rho squared. And so here then the phase transition occurs as a function of omega dash.
So gamma is what you would call like the variable in the so-called scaling window of the transition. So you're saying that for any constant gamma, then we're at some continuous value in the MMSE between 0 and 1.
Yeah, so if you normalize correctly, like gamma equals 1 is where the phase transition is. So when gamma is larger than 1, this is growing so easily that you're on the sort of positive side of the phase transition. But if gamma is less than 1, you're on the bad side of the phase transition.
Oh, so it's not what I said. Okay, thanks.
Okay.
Jump suddenly from 0 to 1.
Yeah, it jumps from 0 to, well, we'll see. I have some plots to show the way that it changes. Okay, so I will mention that the work by Niles Weed and Zadik showed analyzed the statistical phase transition for this problem for a slightly more general regime. So they showed the same critical point of the transition, but they showed it for general decaying rho. However, they didn't characterize the behavior of the MSE, and so we think that perhaps you know the value of the beta is probably a weakness of our proof method, but it's not clear that we can get to the general regime that they show. Okay, so what I want to do is show a little bit of the behavior of these phase transitions with some simulations. So all the simulations are for the Bernoulli signal, but the behavior of the Bernoulli-Rademacher is the same or similar. And so here what I've plotted on the y-axis is the mutual information. And remember, the mutual information is related to the MMSE. So this is giving us information about the statistical phase transition. Along the x-axis, I have plotted changing SNR. And it's relative to the critical point, which is given by this negative log rho over rho. And then the lines in the plot correspond to different sparsity levels. So we're interested in the sparsity decreasing. So the least sparse signal is the blue curve, and then the most sparse is the red curve. So the red curve is like rho is like 10 to the negative 20. So we're very, very sparse here. And then as the sparsity changes, so does the problem size. So, okay, so what we're seeing here, right, is kind of in this limit of vanishing sparsity, what's happening is as we change the SNR, up until a point, right, your mutual information between the signal and your data increases linearly, right? So as you increase the SNR, you get a linear increase in your mutual information, but up until some critical point, after which you kind of get an angular break in the plot. So that suggests that, in this limit of diverging sparsity, after you increase the SNR beyond that critical point, you don't get any more, or you don't add any more to your mutual information. And so then using the MMSE relationship, we can translate those results into results about the MMSE of the problem. So again, x-axis is increasing SNR, y-axis is now the MMSE for the problem, and the plotted values are decreasing sparsity, with blue is, you know, the least sparse, and red is the most sparse. And so what we're seeing here, right, is now we get this sharp jump in the MMSE as we go to this vanishingly sparse situation, right? So if we're on the smaller side of the SNR of that threshold, then our MMSE is going to take the value of 1, which is kind of its maximum value. And on the other side of this threshold, it jumps down to 0, which is the minimum value. And so a similar phenomenon occurs for the MSE of AMP. So this is related to our computational limits, right? So again, plotted the SNR on the x-axis, but now the critical value is different. It's the threshold for the AMP algorithm. The y-axis is my normalized MSE of AMP, and I'm plotting decreasing sparsity. So my colors have changed a little bit here. So rho is like the least sparse, and black is the most sparse. So as we're you know, getting more sparse, then this sort of sharp 0-1 phase transition shows up again for the MSE of AMP. And so I will note that here for the actual constant where the critical value is, we approximated that numerically, but it's been found in some other works as well. Okay, and so just as a final plot, here's a look at what this says about the gap between the computational and the statistical limits for the problem. So here the dotted lines are the AMP performance, or computational performance. The solid lines are the MMSE performance, and again, black is the most sparse, and red here is the least sparse. And so the computational to statistical gap is represented by the horizontal sort of distance between the two lines. So we can see that the sort of two green lines here, they're closer together than the blue lines and then the black lines. So the computational to statistical gap is diverging as we become more sparse. And so, you know, in fact, right, we sort of characterize, at least when rho is going to 0, you know, slower than log n over negative alpha, this gap is determined by the difference between these two critical points. And so we'll mention that, you know, we think that this gap still holds for the sort of tighter regime where we prove the statistical limits, but controlling the AMP limits was fairly difficult. And so we weren't quite able to get to the regime that we wanted, and this is left for future work. And so just to wrap up.
Cindy, can I ask the question? This is David.
Yeah.
Yeah, it's on the previous slide. The critical threshold for the statistical critical threshold is exactly same as the one in a proportional regime where rho n is just a small constant, and it's a linear proportional regime. But curiously, we have a square root there appearing. So I don't know if it's just mismatch of the different parameterization or what else, but I'm just curious. It's exactly square root of 4 log rho n inverse log rho n, and which it should be the case, except for the square root shouldn't be there. I'm just curious why there is a mismatch. Maybe you know.
Yeah, no, offhand I don't.
Different. Okay, Elias is saying a different parameterization. I'm trying to understand.
Yeah.
I think you probably defined this and
right, yeah.
the square root, right? Yeah.
I think, yeah, it's probably just this, right? So.
Okay. That helps. Thank you.
Yeah.
That helps. Although I should reinforce something that you already said, that in the proportional regime, certainly it would not get all or nothing behavior. It will be just a partial recovery above the statistical threshold.
Okay. Thanks, David. Virtual David. Okay, so to wrap up, I will just use like 2 minutes to tell you some notes on how we actually do this to get to kind of the meat of the talk. So, okay, so for our theory, we'd like to show exact thresholds for these all or nothing transitions. And so for the statistical limits, we do this by giving a rigorous derivation of the asymptotic mutual information in the form of a one-dimensional variational problem. And then for the computational results, we use a finite sample analysis of approximate message passing, which rigorously allows us to track its performance in these sparse regimes. So in just a little bit more details, okay, so for the information theoretic limits, the idea is that we use a method called the adaptive interpolation that tells us how to compute this mutual information between the signal and the spike. And it gives us this mutual information in the form of this one-dimensional variational expression. And so adaptive interpolation is a method that's been used to show these sorts of information theoretic limits for these sorts of problems in the linear sparsity regime, in particular by my co-authors, Jean Barbier and Nicolas Macri. And it kind of wasn't obvious a priori that this could be sort of used in this sort of sublinear sparsity regime, but they were able to make it work. And so then once we have this variational expression, this is something we can at least solve for the Bernoulli and Bernoulli-Rademacher signals, and then by differentiating it and making use of the MMSE relationship, this tells us something about the MMSE of the problem. And so then we get these sorts of closed form values of the MMSE, and we can look at their limit, you know, as n goes to infinity. For the computational results, as we mentioned, we analyze an appropriate approximate message passing algorithm for the problem. And so a nice feature of AMP is that its performance is characterized through its state evolution, which is a deterministic recursion. And so sort of the challenge here is that, you know, in the setting where rho is a constant value, when it's constant with respect to n, then you can use the asymptotic AMP theory, so the standard AMP theory, to analyze the performance of the algorithm. However, when rho is changing with n, you need sort of a finite sample performance of the AMP. Do you want to? Oh, okay. So when rho is changing with n, you need instead sort of a finite sample analysis of this algorithm that demonstrates concentration around the state evolution predictions instead of like the asymptotics of the situation. And so then once you have those concentration arguments, you can use the state evolution to characterize this MSE performance. And the real sort of technical challenge here is you know, when I originally studied the concentration for the AMP algorithms, I treated, you know, a lot of things like it's the state evolution and the constants associated with the Lipschitz denoisers in the algorithm and so on as universal constants with respect to the problem. However, here, all of these things now change with n because they depend on this SNR or the sparsity. And so you have to kind of carefully track how all of these things influence the concentration of the AMP algorithm. And so once you can kind of incorporate all of those values, all of those things that change with n now into the rates of concentration, you can say something about the MSE performance. And so I'll stop here. Thanks, Simon.
Great, thanks. Any questions?
This time I'm not just stretching.
Yeah.
So the number of iterations of AMP is little o of log over log log. And I guess this isn't the regime in which I usually think, but how many iterations do we really believe AMP ought to have? I would have thought it would be more like log.
Yeah, so I think you're right. So this is Yeah, this is something that's haunted me for a long time now. So the reason that we have that statement is because the T shows up in the rate of concentration. So T being the iteration number. And so in order for like the concentration that we show to be, non-negligible, you aren't bounding probabilities by one, you need that T grows much more slowly than N. Right. So in some sense, the finite sample version is kind of just a refined asymptotic statement because it shows you how all of these things now grow to N together. And so now we've added some other things like changing sparsity and stuff that grow within. In general, yeah, I mean, I think for any actual, like, if you use AMP on a real problem, log n over log n is going to be like very small. So, I'm not sure how much use those finite sample guarantees are for like the actual applied performance of the algorithm.
Sorry, and yet you showed results. You showed results showing that AMP does achieve a low MMSE with that small number of iterations. That was one of the graphs you showed, or was that its eventual?
Yeah, so there, okay, so there, when the row is really small, you need the N. So what we plotted there was actually the theoretical performance of the AMP. So it wasn't like an empirical simulation, but in those situations, when rho is getting small, N is getting big, right? So,
Can I ask something also? If possible. Do you hear me?
Yeah, go
Yes.
for it.
Yeah. So thanks a lot, by the way, for the nice talk. So I'm a little bit confused about the AMP result. Like you said that it holds when the sparsity is at least 1 over log to the alpha for some alpha bigger than 1.
yes.
Is it what you said? Why alpha bigger than 1? Like, isn't it like, I'm a little bit confused, yeah. Like, because if, right, I mean, if it's holds for anything else. Like, is it a type or just?
No. So it could be any alpha bigger than 1, I guess is the thing. It just can't.
Like, if it's big, like, then alpha less than 1 should work also, right? Because it's bigger than. So, am I missing something? So, 1 over log n is bigger than 1 over log n squared.
Right. So you can pull that constant up to make it as quick with respect to kind of the log n decay as you want, but it can't be like. I mean, eventually you're never going to get to like into the negative b, even if you increase that alpha a lot, right?
Yeah, no, I'm talking about the other direction. So somehow, like, I mean, I got. Okay, I'm saying probably your result works for any power of logarithm. So if it's 1 over log n to some power, this should work because it's. I don't understand why, like, the powers.
Sure. Yeah.
So somehow, like, it's not that something magically happens if it's order 1 over log n.
Sure. Yeah.
Okay, and you said that, like, you believe it's probably true if it's below like this, but you just didn't have you didn't prove it, or like you could conjecture that the all or nothing calls for AMP even.
Yeah, so we think that we should be able to get the same guarantees for the AMP, like in the same regime as the statistical guarantees. So like, you know, rho grows more slowly than into the negative beta, but I haven't been able to like sort it out yet.
Yeah. Okay. Thank you. Thank you very much. Thank you.
You have a quick question along the
Sure.
same sort of line. So first off, I mean, yeah, really impressive results that they're so sharp and so forth. But yeah, I'm curious about the sparsity. Also, maybe this is the same answer as Chris's question on the number of iterations. But where does this enter? Are things just not concentrating enough when you go to lower sparsities?
When you go to
Like does the state evolution, like if you say rho is, I don't know, like, you know, n to the -1/3 or something like this, like where does this show up in the AMP analysis?
Oh, right. Yeah. So essentially you get a rate of concentration that, you know, within that rate, things like the state evolution constants or the Lipschitz constants of the denoisers and stuff all show up. And, that those things are all related to lambda and rho. And so if you had, rho like into the -1/3, then, what you find for that concentration is that you're kind of just trivially bounding it. It's not a small probability anymore. It's the probability that the AMP algorithm deviates from its state evolution is no longer small. It's now something like 1. So it's just the way that all these things kind of show up in the rate of the concentration of the AMP around its state evolution.
Okay. So there's this paper of Deshpande and Montanari that you cited, and they analyzed, I think, AMP for planted clique. I'd be curious. I mean, because there it's like severely sublinear sparsity. It's closer. They get root n sparsity. I'd be curious to revisit that. I forgot the details of what's happening there. Have you looked at that? Can you compare what's happening?
Yeah. So I can't quite remember the details of that.
Yeah, so that one is not exactly analysis of AMP. It's actually using the moment method.
Yeah.
So it's slightly different.
It's a different algorithm, right? Because it's related to what you guys did as well, right?
Sorry, I just want to clarify that, like in this, Deshpande Montanari's paper about planted clique, so they are not exactly analyzing AMP. They're analyzing actually more like a pre-propagation algorithm. So they are using moment method, try to compute moments, so that allow them. But then they also analyze only the fixed number iteration, and then they use the further spectrum method to boost the signal in the end, I think.
Sure. Yeah.
Okay, and you have a paper that extends this to the planted.
Oh, yeah. So we kind of follow that approach and then analyze that for the submatrix estimation problem. Yeah, so we also use the moment method.
But jamming, do you get estimates on the nothing aspect in your result?
No, at that time we are not looking at all or nothing. So.
But you didn't have any understanding of failure of AMP below the threshold of any sort.
I don't recall. I don't know.
Okay. Yeah. Thanks a lot.
But like, for example, y'all's paper got the lambda equals 1/e to the rho. Like they'd already found that threshold. So this goes back to.
Oh, okay.
again.
Okay. Now I see the
Yeah.
connections. Okay. Yes.
Okay, cool. Any other questions? Let's thank Cindy again.
Thanks.
So I guess that's it for today.